So as James said, I'm Tim Lee. I write a newsletter about AI, and I've got 3 great panelists who are experts on robotics, and I'm interested to hear what they have to say. So let's start with Adrian here at my left. Adrian and I have known each other for quite a while because he was at Cruise for many years. When I was at Cruise, he didn't tell me any secrets, but I know he was like a reader of some of my articles. We would chat periodically. And then in 2021, he left Cruise. And so he was there, I think, since 2016, so it was pretty early. Saw a lot of the early growth, the acquisition by GM, et cetera. But then he left in 2021 to start a company called Foxglove. Adrian, tell us what you did at Cruise, why you decided to leave, and then what the vision for the new company is.
Yeah, absolutely. So Adrian Macneil, founder, CEO at Foxglove. Foxglove is a company that builds infrastructure and developer tools for the physical AI industry. At Cruise, so I was at Cruise from about 2016, joined when there was 30, 40 people, a couple cars that could turn right and could not turn left. And then we did a lot of work, right? We had to build from scratch this entire pipeline. I like to think about the machine that builds the machine. How do we build all of this infrastructure and tooling that lets us capture and learn from all of the driving that you're doing out there in the real world, turn that into insights that allow us to develop vehicles that then can drive around autonomously. And so that was really the thesis behind Foxglove, that coming into 2021, hey, that's cool. We made cars that can drive around San Francisco. What about everything else that we need to automate in the world? And so that was really the thesis, is how can we take this same developer platform, the same type of infrastructure and tooling, bring that into the physical world?
All right, so then we've got Mikell Taylor. She spent more than 5 years at Amazon working on warehouse robots, I think, primarily. And then just last year, she went to GM. So actually, since you spent so long at Amazon, and I know there's some overlap between what you're doing there and the AV industry, talk to me about what you did at Amazon and then what the new role is.
Yeah, so at Amazon, I led the Proteus Autonomous Mobile Robot Program, so the first of the mobile robots to go outside of the fences that Amazon had. And then now at GM, GM does obviously a lot of automotive manufacturing, pioneered the use of robotics in automotive manufacturing decades ago, and now we're working on leveling up with all of the new advanced technologies available.
So talk about a little bit more the Proteus robots. They're like, I don't know, they're like this big, right? And they move like shelves around. Is that?
Yeah, so they move carts around. So the original Kiva robots that Amazon acquired move shelves, and this is about moving carts. But this is in an area, it's like the dock after your package gets packed up and sorted by zip code into a cart. Those carts have to go on a truck. And moving the carts from where packages get sorted to the truck is a lot of walking. I have done it for a shift. It is a lot of walking. And so we thought, hey, robots could do this, but they got to be around people because there's also people pulling pallets. There's people doing other work in that area. We can't fence this off. What do we do? And that led us to really push toward this kind of collaborative autonomous mobile robot system that could be out among people.
And so one of the things you said when we had a prep call to kind of talk about what to talk about here, and one of the things you said that I thought was really interesting is with AVs traditionally, the goal is to never interact with the world. Like you want to not hit people, not hit objects, et cetera. But in the factory, almost by definition, some of these robots need to, pick up parts or cut something or paint something or something. It's like doing something in the physical world. Talk to me about that transition and how it makes the problem different from what a lot of the people in this room would be working.
Yeah, well, that's the thing is to add value in an industrial environment, you have to do something other than move, right? And so that picking up of a cart is a different kind of autonomy, a different kind of behavior than the driving around not hitting things part, right? Which is also important. So we were able to pull a lot from what the autonomous vehicle industry had learned, right? And a lot of the kind of cartographer tools out there and Foxglove tools and so forth. And there was a lot we could pull from that, but nobody had really figured out okay, but what do you do when you get to where you're going? How do you touch a thing? How do you get into a different mode? How does the safety system change when you're ready to do that? And that was a lot of the space for innovation for Amazon, for sure.
Mm-hmm. All right, and then finally we have Avinash, who also has kind of a storied career in AV. You were at Uber ATG early on, and then you joined Toyota, where you were part of the fairly early self-driving team that spun off into Woven, but you did not go in the Woven team. You stayed at Toyota and are working on other aspects of robotics, in particular on collaboration between humans and robotics. Talk to me about that work. How does that work, and what are the challenges in getting humans and robots to work together collaboratively?
Yeah, great. Thanks for that kind introduction. So yes, my role at TRI is really kind of focused on how people and sort of these intelligent machines that we interact with every day can have sort of a new kind of paradigm of working together. And so the most obvious one that we started with is cars. Cars are generally the most intelligent machines that people interact with. And I think like some of our other speakers have mentioned before, there's not just full autonomy systems that are out there. There's also systems where they're highly autonomous vehicles that you want the driver to kind of engage with in some way. So something like level 2, level 3, et cetera. But also systems which are where the driver is actually engaged in driving and the car is intelligent. Is there ways that we can create new value through that? And so that's one of the things that we're looking at. And then when we started doing that, we realized there were a lot of learnings that we could take to that we could expand to other kinds of physical AI systems, which I think is a common theme here. If you think about cars, they're really kind of the first large deployment of robots in a kind of uncontrolled, out in the world kind of setting. And because of that, learning how to understand other humans, whether they're pedestrians or other road users, understanding how to interact with them, all those lessons we think can also be applied to other forms of physical AI as well, where, like Mikell was just mentioning, the interaction element becomes a lot more important.
It seems like one obvious application to this is in ADAS systems, where the human's mainly driving, or maybe the computer's mainly driving, but it's really important for the human to understand what the vehicle is doing and to understand what actions can I take safely to guide the robot, guide the ADAS system without getting in the way. Is this something you've been focusing on recently?
So more recently, we've actually focused on a slightly different paradigm. So if you think about the levels of autonomy, there's kind of this general trend that as the systems get more autonomous, the human gets less involved, and then you kind of have this handover problem between, okay, now when does a human hand over to the AI and vice versa. So we actually did investigate that for a while, and there are lots of challenges around things like that. But we started thinking about, well, imagine a system where the AI is very performant in the car, but the human is still completely engaged. What would that new paradigm look like? And so, one of the interesting things about physical AI is that when we think about it, because it's an AI that's in our physical space, the most obvious application is, well, it can just replace a thing that we are doing, whether that's driving or picking up boxes or whatever it is. But maybe there's a way to kind of rethink that paradigm where rather than just replacing the driving tasks in the case of driving, it's actually amplifying us in some ways. So imagine a car, for example, one of the concepts that we're working on is what we call driving sensei, so a car that is actually teaching you how to drive and improving your skill over time. And so you'll get to experience some of this with our demonstration outside. Our vehicle is really about sort of immersing the driver in this kind of AI-driven experience to help them learn different road scenarios outside. The demo is on snow driving. And you can imagine that we can use that to improve people's skill over time. The idea here is imagine you had a teenage child who was learning how to drive, and you could feel confident that your Toyota vehicle would actually keep them safe, but also make them improve in their skill over time. So that's an example of kind of rethinking the paradigm a little bit, where instead of it just replacing the task, we're thinking about what additional value can these systems give in order to actually improve or augment or amplify the person.
So Adrian, one of the reasons I like to talk to you is that since you're running a software platform, you're working with lots of different companies doing lots of different kinds of robotics. Can you give people just a sense for the breadth of the kinds of different robots people are building and the kinds of challenges people are having and how those compare or contrast to what you were doing at Cruise?
Yeah, absolutely. I mean, this goes back to what I said earlier, which is that self-driving was really the first big application of physical AI. We kind of went through this whole learning curve. The entire industry went through this learning curve over the past sort of 10 years of how to put machines in the real world that can think and act autonomously. But when you want to go beyond that, you think about, well, what are other applications where we can automate machines that are out there, right? And if you look at sort of the history of robotics, there's been all through the 2010s, people were trying to do this. And there was the Kiva thing with Amazon, and Amazon managed to deploy a lot of robots. But we kept running into these challenges of, they were not intelligent enough to start doing all of these really complex tasks like manipulation or interacting with humans in a way where behavior is important. We then reached this kind of curve, sort of early 2020s, where the AVs got good enough, right? They were able finally to be able to negotiate intersections and four-way stop signs and roundabouts and all of these kind of things. And that those same lessons that we learned about how to build that was really about getting robots out in the physical world, getting them out in the real world, collecting data from it, finding interesting long-tail events, not just lots of driving along straight roads, but how do we find these interesting events, and then how do we take those kind of lessons and turn them into test cases and use it to improve the overall system. And so once we kind of figured that loop out, now we're seeing the past like sort of 2-3 years, this just like massive proliferation of companies across agriculture, construction, logistics, drones, underwater robots, ocean surface robots. We're seeing self-driving tractors and self-driving forklifts and self-driving lawnmowers, and we're also seeing a huge amount of manipulation type stuff has sprung up recently, right? We're seeing, obviously, everyone thinks about humanoids. There's a lot of awareness about humanoids, but you don't necessarily need legs to take advantage of all of the lessons that are being learned in manipulation. So we're seeing now a lot of these robots that can pick and place things and can sort packages on a conveyor belt, and yeah, just an enormous explosion. If there's one thing I could get across is how broad this array of kind of autonomous machines is, right? You've got everything from those indoor conveyor belt type tasks, you've got navigation type tasks where you're moving around, through to John Deere recently announced their See and Spray product, where they've got autonomous sprayer, which is only putting on herbicides and pesticides when it's over top of weed, but not when it's over top of crop or things like this, right? Where it's just turning on and off sprayers, but it's still, we're using machine learning, we're using computer vision, we're using autonomy to actuate those devices. So yeah, it's a very broad industry.
So how much overlap, how should I think about conceptually? You've got navigation robots, which is AVs, but also, like you said, forklifts and the Proteus robot. And so,
yeah.
And then you've got manipulators, which are maybe not mobile, may or may not be, but they're mainly picking up. Should I think of those as basically different categories in terms of the kind of tools you need or the kind of problems you're solving? Or is there enough overlap that it's really all, I'm sure it's somewhere in the middle.
Yeah,
what's similar and what's different?
So I mean, all robots maybe you could think of as you're either navigating something or you're manipulating, you're either navigating the world or you're manipulating, or both, right? This is kind of a very high level breakdown. A lot of the things when we go from self-driving, I guess Michael's point, right, is self-driving, we didn't really have to interact with things. It was kind of behavioral interactions like stop signs, but there wasn't actually grasping and touching objects. So there are differences. For example, simulation is a completely different problem if you're dealing with actually manipulating deformable objects or something picking up a t-shirt is a very different problem from simulating a road. On the other hand, a lot of the way that people are training these new robots, so the way that we're training, using ML to teach robots how to interact with things, the data loop looks very similar. The way that people are out there collecting data about how robots are performing in production, finding edge cases, that piece is very similar regardless of whether you're doing, indoor vehicles, outdoor vehicles, manipulation type things. So, it depends on the specific task, but it's probably more carryover than not, I would say. A lot of the similar kind of approaches are being used.
Is simulation an important part for these kind of long tail, these smaller companies doing kind of niche applications? I mean, I know a company like Waymo, they have a huge team and a ton of data, and they can make this really sophisticated simulator. Does that work if you're building a lawnmower that I assume is much smaller, market value?
It's a good question. I think simulation is really important when you're trying to build a safety case, or when you're dealing with just very high accuracy tasks, right? Driving is a very high accuracy task. You need many nines of reliability. You cannot afford to make even the slightest mistake, and you can't afford to just every time you've got several lines of code change, we can't afford to go drive another 1,000,000 miles to validate it. Or now industry leaders are at tens of millions of miles before they hit some of these kind of long tail edge cases. So it's not possible to drive enough miles in the real world to validate every single change. So simulation is very important. On the other hand, like a lawnmower, or I've seen people build lawnmowers or indoor robots and things like that with no simulation because they're moving at 3 miles an hour, and if something goes wrong, it's not that bad, and also the set of kind of scenarios that they might run into are limited. I think ultimately simulation is very, very important in AV and in physical AI more generally, but there are definitely applications that are simpler where people are just getting away with not simulating.
So Michael, something you told me that I thought was fascinating that I did not know about is that for robots that interact with people, there's pretty strict regulations about how quickly they move and how much force they apply and things that there's a pretty different way of proving that a system is safe than we have in the AV industry. Can you just walk through people? I bet a lot of people, I haven't heard, I bet a lot of people are not familiar with that. How do the kind of factory robot setting, what do you have to prove to demonstrate that it's safe to operate a robot around people, and what are the kind of standards that apply there?
Yeah, there's a handful of standards, but they all eventually go back to the concept of functional safety, right? Which is you assess your specific thing in your specific environment and task, and you figure out what are all the things that go wrong, and how severe are those things, right? How often would a human be exposed to that situation, and how severe are the consequences if that situation did occur? And then based on that, mathematically, there's an abstracted mathematical analysis that says, okay, well this, you can just tell people, hey, don't do that. But this, it needs to be a fail-safe design in the robot that prevents it from becoming an unsafe situation. And that's where stuff gets really challenging. It is especially challenging because currently under those regulations, you cannot use a non-deterministic algorithm for any of those functions. And so for example, when you're doing obstacle detection, all obstacles have to be treated the same. You can have an ML layer that can say, this is a human, this is another car, this is whatever, but you can't use that in the safety loop. And so you have to treat the stack of pallets that's not going to jump out in front of you as potentially being a human that's going to jump out in front of you. So that makes the problem a lot more challenging, especially when you do have to touch things, right? How do I know that that's the thing I'm allowed to touch and not maybe a person? That's what presents a lot of really interesting engineering challenges to a development team. And it goes all the way down, not just to how you're implementing these behaviors, but also in your selection of the hardware, the processor that is going to do the safety level processing, what communication protocols you can use with your sensors, how you develop the software, which language you use. And that all gets vetted as like an engineering process, along with how good are your self-diagnostics, can you demonstrate certain capabilities against the regulations through a testing period and certification. So that's a space where simulation can be really helpful, but it's not sufficient to prove. There's a different way that they do the sort of certification testing. But we still lean heavily on it to assure ourselves above and beyond the industry standards that, yep, we're going to be okay.
Right. That's really interesting. So I've been thinking about our title, this AV Dividend, and one of the most obvious, I think, aspects of this is that the AV industry really helped pioneer 3D LiDAR as a technology. Mikell, could you talk a little bit about how widely is LiDAR used in factory or warehouse robotics? Is it similar, different, and kind of what's the role of LiDAR in the kind of applications that you're working on?
Yeah, LiDAR is a really popular sensor to add on to an autonomous mobile robot, right? It's used less, I think, in the manipulation robotics that I see, but much more in the autonomous robots. And it serves a couple of purposes, right? One is for SLAM navigation, especially 3D LiDAR can be really, really effective in your kind of SLAM map of the world and your navigation accuracy. It can also be used as a safety sensor. What's been interesting is that, part of what I forgot to mention is that generally in industrial robotics, you have to use safety certified sensors, right? Which is a very expensive process to design them the right way and also to get them certified. But recently, around the time that 3D LiDAR started becoming a sort of commodity, the regulations allowed for, okay, well, if you don't want to use a safety rated sensor, if you can prove to us that you have an architecture that has sufficiently diverse sensing modalities, that they don't all fail the same way, and redundancy built into all those modalities, you can use non-safety rated sensors. And that really allowed the LiDAR market for autonomous robotics to explode. Suddenly now we could use these sensors that weren't a very expensive ZIC 2D LiDAR. We could use all these really cool 3D LiDARs that were being developed for the automotive industry. And they were really excited to find a new market. Then there's an interesting thing that happened around like 2021 where the autonomous vehicle industry kind of got into a little bit of a trough. All of these manufacturers were like, oh my gosh, AMR market, how you guys doing? So we got a whole lot of attention, a lot more stuff built to our specifications, which was incredibly valuable as a robotics industry.
Yeah, that's cool. All right, so Avinash, you were saying before that that you think a lot about the kind of interaction between humans and robots, and it seems to me one of the lessons that the AV industry has learned is that it's really important not only that the robot can understand what the human is doing, but you want the human to understand what the robot is doing, and for the robot's behavior to be understandable and predictable. Talk to me about that. How that has spilled over into the other kind of non-AV robotic applications.
Yeah, I think so that's an excellent point, right? So I think one of the things that we're seeing, especially as a marker for people trusting whether it's a autonomous car or robot, is an ability to understand what its goals are and to make sure that they feel like that's aligned with the human's goals or the person's goals as well. And so making sure that communication layer, I think, has been really important. So one of the interesting things about cars is the way that you've interacted with a car hasn't really changed for about 50, 60 years, right? You've got a bunch of lights, you've got a bunch of sounds, but the cars themselves have got a lot more intelligent, and actually the bandwidth of communication that we want is actually much broader than it used to be, because the cars used to tell you very simple things. Now they're trying to communicate much richer, more diverse information about the scene, about what they're intending to do, et cetera. And so we've been really at TRI investigating new kinds of modalities in which we can do that. Obviously, a lot of the improvements that we're seeing in language models are helping us with this. You can imagine that your car is now able to actually explain to you what it's doing, or when you're driving, explain to you perhaps ways in which that you should change your behavior in order to improve safety or things like that. But you can also imagine other kinds of immersive experiences, right? VR, AR, other kinds of interactions. But what we're trying to do is sort of broaden that pipe of communication between the robot or physical AI system and the person in order to do that. I think what we're seeing in general, though, is like a lot of these systems. So if you think about the first commercially viable autonomous system, that was in 2005 in the Netherlands, autonomous shuttle. It was revenue generating and a closed course, so no other road users were on that road. But the real kind of unlock here is when it can go out into the environment, like like we see now with all the beautiful robotaxis outside. Once you're able to actually interact with the world, you can do a lot more things of higher value to the person. And so I think this is kind of one of the big lessons we've learned from AVs is that we want our physical AI systems to be able to go out, get out of these more or less more controlled environments and get out into the real world where they can add sort of more value and ideally create more business opportunities for everyone. And I think some of the lessons that we learned from AVs in that, both in the business and the technical side, I think on the business side, we're learning that basically autonomy doesn't have to be everything. You can actually have, like we saw in cars, full autonomous systems, as well as these highly automated systems, L2, L3, other kinds of value that can be created. And so we can be creative about how we think about these things. And then on a technical aspect, I think what we're seeing is when you put these physical AI systems out in the world, you shouldn't expect the world to adapt to you. Your systems have to become more naturalistic, more human-like in order to adapt. And so, the example I would choose here is, if you had a AV that was following all the laws at a four-way stop, it would just never move, right? So we actually, through data, have to learn about how these things happen. And I think at TRI, we are really seeing that this human-centric design for the systems, thinking of the human in the loop, and also sort of human-like behaviors are really important. And so we're kind of pushing the forefront of that because we think those are really big open research questions.
Very cool. So one of the other big challenges I think the AV industry has had is having remote assistance for vehicles. And Mikell, we were talking about this on our call. I know most factory robots don't have remote assistance, but you do sometimes have to have a human step in when the robot doesn't know what to do. Can you talk to me about how that often works? I'm sure it varies by the robot, but what's a typical way that works, and should I think about it as a similar kind of thing to the way that works with AVs, or is it like its own kettle of fish?
It can vary, but I think that the core thing that we try to do in the industrial environment is treat it like any other piece of equipment, right? It's just equipment. It's cool, it's a robot, but it's just equipment. In the same way that if a conveyor goes down, right, somebody's light lights up at their desk to go and fix the conveyor, same thing happens with the robot. They can come over, they got a little, video game controller that's like, I need to move this out of the way and do something to it, or it just needs a reboot, I'll take care of that. So really kind of looking at that intervention like it's another piece of industrial equipment that is staffed by the tradespeople in the plant.
That makes sense. All right. Well, we are out of time. Thank you all for sharing your expertise on robotics.
Thanks for having me.
Thank you.